welcome to the second video on neutralization reactions. And when we did our unit on chemical reactions, we learned a little bit about neutralization reactions, so some of this is going to be a review. At the end of this lesson, there's some math, and what I decided to do is pre-write the math, because otherwise you're going to spend a lot of time watching me write the math. But I really suggest when we go through the math that you also go through it too. If you watch passively when we're doing the math part of this, you're totally not going to get it. Alright, so let's begin. So, neutralization reactions are when an acid and a base react completely. So equal moles of acid and equal moles of base react completely to produce water and a salt. Okay? And remember, a salt is an ionic compound. Okay? And it involves all the time the combination of the OH plus ions from the acid and the OH ions from the base to generate water. Okay. Now, what a misnomer, okay, is, okay, depending upon if the acid is, if you're missing a strong acid with a strong base, a strong acid with a weak base, or a weak acid with a strong base, at the point of equal moles of acid and base, the pH is not always 0. So not always 7. Whoa, 0. Hi, Kaiser. So, for example, if you have a neutralization reaction between a strong acid and a strong base, when you have equal moles of acid and equal moles of base, the pH is going to be exactly 7. Okay? Now, and we're going to see the reason why in a second. Okay, if you have a neutralization reaction between a strong acid and a weak base, when you have equal moles of each, the pH is actually going to be below 7. Okay? And then if you have a neutralization reaction between a weak acid and a strong base, okay, then the pH is actually, when they're equal moles of each other, okay, the pH is actually going to be above 7. Okay? And on the next slide, we're going to see why. So here we see the reaction, okay, between this is a strong base and this is a strong acid. Okay? And if we see it's sort of like a double replacement reaction. If we react equal moles of NaOH with equal moles of HBr, we get NaBr and water, a salt and water. And at this point, when all the moles of base have reacted with all the moles of acid, if you have a strong base and a strong acid, the pH is 7. And why is that? Well, if you take a look at this salt is composed of two pathetics. Okay? Both Na and Br cannot act like an acid or a base. So when this salt is in water, NaBr is in water, it does not affect the pH. So the pH is neutral. Now if we scroll down and look at the reaction between these two, so HBr is a strong acid and NH3 is a weak base. If we take a look at that reaction, remember this, when we looked at our previous slide, we said that this pH would be below 7. Okay, and let's see why. When we do this reaction here, this reaction is a little bit different from the other ones. So HBr is going to act like an acid and lose its H+. And NH3 is going to act like a base and accept the H+. And then we produce the ammonium ion and Br-, because again, this lost its H. This was a little bit different than here. We're actually not producing water, but we're producing a salt. NH4Br is a salt that dissolves in water. Okay, now, why is this acidic? So remember that when we're saying that we react equal moles of a strong acid with equal moles of a strong base, we still get a solution that's slightly acidic. And the reason why is, well, this is a pathetic, right? This is an anion that's a pathetic, so it can't act like a base. But this, okay, can act like an acid, okay? It's the conjugate acid of a weak base, okay? And this can act like an acid. So therefore, when it's dissolved in water, it will lower the pH a little bit. Okay. Now, if we look at the last one, okay, the last one is a reaction between NaOH, which is a strong base, and HF, which is a weak acid. Okay, and if we look at the reaction here, let me move it up out of the Smortborg limited mode bullshit. So if we look at that, okay, so here we have a double replacement reaction between NaOH and HF. If we take a look at what's produced, obviously we have water here, but then we have sodium fluoride. And sodium here, that's a pathetic, right? It's a cation, okay, but it doesn't have the ability to act like an acid. But then we have F, okay? And F is not pathetic, F has the ability to act like a base, right? It has the ability to take H+. It's not from one of the strong acids. So therefore, when you mix a strong base with a weak acid at exact molar quantities, you'll produce this salt. Okay, but the anion of this salt has the ability to act like a base, so it's going to raise the pH a little bit. The pH won't be exactly neutral. So here are problems that we actually have done before, where we're going to determine the amount of acid or base, or the volume of acid or base needed for neutralization. We've done these, and so here we're calculating the volume needed to neutralize this amount of nitric acid here, and both of these are strong acids and strong bases. So the steps are to write the overall neutralization reaction, and then write the net ionic. You don't really need to do that, but the AP exam is obsessed with net ionic, so I'm going to bring it back. And then we're going to use this formula, which we've seen before, to calculate the amount of in this case, potassium hydroxide we need to neutralize this amount of nitric acid. So I wrote the neutralization reaction. Remember, this is a double replacement, so you can make sure you can do that yourself, right? And here we have, again, this salt. Both of these are pathetic, so again, the pH is going to be 7 when you react equal moles of KOH and HNO3. And here I wrote the net ionic. So let's go over the net ionic writing a little bit again. So this is a strong base, so it ionizes completely into K plus and OH. And this is a strong acid, so it also ionizes completely into H plus and NO3. This is a soluble salt. If you remember your solubility rules, nitrates are always soluble. So this completely dissociates into its 2 ions. And water's a liquid, it just gets brought down. And if you remember, what we do is we cross out what's common. So the potassium ions are common, and the nitrate ions are in common. And we're left what we have down here, which is H plus OH produces water. And again, this is true, this net ionic is true whenever you mix any strong acid and strong base. So now we're going to use the equation, okay, MAVA equals MBVB, to calculate the volume of this that you need to complete the neutralization. And you see I inserted the values, so we have the amount here, the molarity here, and the volume here. I converted to liters because this formula needs in liters, so you see that that's done here. And then I have the molarity of the base, which is done here. And now you would get your calculator out, which I already did, and do the division. Okay, and you would get 0.0368 liters. Usually it wants the answer in milliliters, so I move the decimal place over to 3 places, and it's this many milliliters with 3 sig figs. Okay, now, make sure you know how to do this. Like, I know I just talked through this, but you really should make sure this math, you know, you can insert the values into this formula yourself and do it. Okay, now, so here we have a similar problem. The only thing that we've changed is now we're using nitrous acid instead of nitric acid. So here we have a weak acid. Okay, and actually, if you go back, look, the numbers are the same. So here I wrote the double replacement reaction. Now the net ionic, okay, is going to be a little bit different. Okay, so here this dissociates completely. It's a strong base. This does not. So this does not get written out into its ions because it's a weak acid. We bring water down. We always bring water down. And then this is a soluble salt. Anything with group 1 always dissolves. So we set it up. Now we're going to cross off the things that are common. And we see that the only things that are in common are K+. So this here, now, so the net ionic is everything with the K+ crossed out. So again, the net ionic is different. However, the process of solving for the quantity of base required to neutralize it is the same. And you actually, again, the numbers here are the same. If you go back to the numbers, you actually get the same answer, which we got here. And I can show you, I typed out the insertion of the work this time. Now, why? It doesn't make any sense. This is a weak acid. Why would you get the same? Well, what happens is like this dissociates completely, and this only dissociates a little, okay? But then these two completely react to produce water and NO3, and then now this can dissociate more, okay? And it will dissociate until it's completely reacted. So once you sort of neutralize some of this, or it gets neutralized, it will then dissociate more, and it will dissociate until it's completely gone. So these problems, whether you have a strong acid or a strong base, a strong acid reacting with a strong acid, or a strong acid reacting with a weak base, or the other way around, the answer is the same. Because once the amount of this that ionizes is neutralized, okay, it's going to ionize more, and it will ionize until it's completely used up. So the answer ends up being the same, no matter whether you have a strong acid with a weak base or a strong acid with a strong base. The answer ends up being the same. So if we were in class now, which we're not, I would pause and have you do this one by yourself and check. So just so you know, perchloric acid is you wouldn't be expecting the ClO4. Okay. So if I were you, I'd pause this video and try to write the neutralization and the net ionic for the reaction of perchloric acid and barium hydroxide. Okay. So I would pause that and do it now to see if your answer matches. So here is the net ionic, and I'm not actually done yet. I need to add something to it. So I wrote the double replacement reaction. And what's different about this one is barium hydroxide has a 2. So it's not balanced. And you see there's a 2 here. So to balance this, we need to put a 2 here. And you actually also need to put a 2 in front of the water to balance the hydrogens. Because here there are 4 hydrogens, 2 from here and 2 from here, and we need 4 hydrogens on this side. Now that has a consequence. Let me bring this down. It has a consequence for when we're using that formula, if you remember. And this is the net ionic. The net ionic is always the same, no matter how you balance it. The net ionic for a strong acid, which perchloric is, with a strong base is always H plus, OH yields water. Now we're going to use that equation, MAVA equals MBVB, which is here, to solve this. But if you remember, because there's a 2 in front of the acid, we need to put a 2 in front of the base side. Okay, and that on the midterm, any of you forgot that. Okay, now, so again, we're going to insert the values. This can go in here, right? This goes in for the volume. We need to convert it to liters, and this goes in for the of the base, and this actually should be a B because I can't write. So if you look here, I inserted those values, right? And you need to remember to carry the 2 because of the 2 here. And so I inserted those values into the formula. And then if you look, you solve using algebra. This thing shoots out a value in liters, and then you usually have to convert to milliliters. I actually think this ends up being 2 sig figs because of this, so it really should be reported as 210. Okay, but those are problems that we did, and this is just a review of that. But on the midterm, a lot of us forgot about when you have to have a 2 in balancing, you need to put a 2 in this MAVA equation. The next problems we're going to look at are neutralization or incomplete neutralization problems, where you have to calculate the pH when the reaction is not done. And I'm actually going to upload this video because I'm near the end of the time, and I know these are long videos. I promise it's going to end up being like 25 minutes worth of video. But I'm going to upload this and then start the incomplete neutralization video.